This is lesson 2 on DeMorgan's theorem in negative logic. You remember from lesson 1 that this is the symbol for a NAND gate. Notice it's an AND gate with a bubble in the output. And this was the truth table. The output of a NAND gate is 0. You remember only when both inputs are 1. And we write the logic equation as z equals not x and y. Now take a look at this symbol over here. It's a symbol for an OR gate with 2 bubbles on the input. This means that the output z, since these are not operations, they're inverters, the output z is just not x or not y. But let's figure out the truth table. Take a look here. Here's x and y going 0, 0, 0, 1, 1, 0, 1, 1. If we compute not x, the 0, 0, 1, 1 becomes 1, 1, 0, 0. If we compute not y, y 0, 1, 0, 1 becomes 1, 0, 1, 0. And z is just the OR of not x or not y. That means it's 1 if either input or both are 1, and 0 otherwise. But look, this z is the same as this z, so this symbol really is a NAND gate. That is, we can make a NAND gate by drawing an OR gate and putting 2 bubbles on the input. Which means that this logic equation, z, not x and not y, must be equal to this z, which is not x or not y. This is an example of DeMorgan's theorem. And DeMorgan's theorem is easy to remember. If you start with this side, that is a NAND gate not x and y, what you do is you first not all the variables. This x becomes not x, this y becomes not y. You then change ands to ors and ors to ands, so this and becomes an or. And then you not the result. We had a not here, so you would put another not. Well, not is just nothing, it goes away. And so you end up with not x or not y, which is what we had from the previous slide, and this is an example of DeMorgan's theorem. Now, let's go back and take a look at these 2 representations of the NAND gate. This bubble means that this is like an inverter. We can therefore think of z, we sometimes say this is active low. Now up to this point we've thought of 1s as being true and 0s as being false. So this logic equation is like false, false, and the output is true. However, we can think of this as being an AND gate in which this active low, we can think of it as being true not when z is 1, but rather when z is 0. So if you see a bubble, think of being true as 0. In that case, we can think of this as an AND gate in which 2 inputs that are true, the output z is true, but now, thinking this is as negative logic, that is, true is 0. But look, here's a truth table for an AND gate. False, 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 true, true, false, true, true, because these are active high. But the output, if we think of negative logic, this 1 is now false, so this is false, 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 true, which is the truth table for an AND gate. Now let's look at this OR gate with active low inputs and active high outputs. Thinking negative logic, a 0 is true and a 1 is false for the inputs, but the outputs, a 0 is false and a 1 is true. So the inputs are active low, therefore this is really true, true, and the output is true. That's for an OR gate. True, false is true, again an OR gate. False, true, true, that's an OR gate. And now a 1 for active low is false. This is false, false, and active high is false. So you see, this really is an OR gate in which this is negative logic for the input, that is zeros for true and ones for false, and the output is active high, that is 1 is true and 0 is false. Okay, let's take a look at the NOR gate now. Here's the NOR gate we had in lesson 1, where Z is not X or Y. And this was the truth table. Remember, it's a not or, so the output is 1 when both inputs are 0. But we can also make a NOR gate by drawing an AND gate and putting the bubbles on the input. To check it, just make the truth table. For the inputs X and Y being 0, 0, 0, 1, 1, 0, 1, 1, not X, the 0, 0, 1, 1 becomes 1, 1, 0, 0, not Y, 0, 1, 0, 1 becomes 1, 0, 1, 1, and Z is now the AND of these two. That is, it's 1 when both inputs are 1 and 0 when any of the inputs are 0. But a 1, 0, 0, 0 for Z is the same as a 1, 0, 0, 0 here. So it must be the case that Z equal to not X or Y, this NOR gate, must be equal to not X and not Y. Now, this is another example of DeMorgan's theorem with exactly the same rules we had before. That is, we not all the variables, so this X becomes not X, this Y becomes not Y. We change ANDs to ORs and ORs to ANDs, this OR becomes an AND, and we not the result, not goes away, and indeed this is a Boolean identity. We can also think of this in terms of the negative logic we had before. Here's an active low output, so let's think of true as being 0 here. Then this really is an OR gate, where the output, this is true, 0, 0, 0 for the output, is true if any of the inputs are true, but the inputs are active high, so for the inputs a 1 is true, so true, 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 and these outputs are true. 1 is false because it's active low. It works for this one too. This is an AND gate, and we can think of this truth table as being the truth table for an AND gate, where the output, true, 1 is active high, is true only if both inputs are true. But since these are active low, a 0 is true here, so this is true, true is true. Any input of 1 or false will make the output false. So let's summarize DeMorgan's theorem. Remember, it's easy to remember. You not all the variables, you change ANDs to ORs and ORs to ANDs, and you not the result. So it works in any order. So if you start with not X or not Y, not all the variables, not X becomes not X, not Y becomes not Y, OR becomes an and you not the result. And these nots go away, so we end up with not X and Y. We could do it backwards. If you start with this one, not X and Y, not all the variables, X becomes not X, Y becomes not Y. Change ands to ors, and not the result. This goes away, you end up with not X or not Y. So it just goes backwards. Suppose you started with not X and not Y. Same rule. Not all the variables, change ands to ors, and not the result. Again, the not-nots go away, and you end up with not x or y. And finally, you could go backwards this way, start with not x or y, not all the variables, change ors to ands, and not the result. So not x or y is equal to not x and not y.